very good evening. I am Surmi Rasya Salim, Faculty Coordinator, ASCE Student Chapter, Manipal, Dubai Campus. It's wonderful to have all of you here with us today for the highly anticipated Tech Talk of the School of Engineering and IT. Through the School of Engineering and IT's Tech Talk series, our goal is to invite experienced professionals from the industry to deliver talks that are idea-focused and provide the upcoming engineers an insight into the broader industry ahead and to foster learning and inspiration. This Tech Talk being organized by the ASCE Student Chapter, it's our immense pleasure to have Mr. William F. Baker with us today to speak on the topic Burj Khalifa and the design of tall buildings, all the way from Chicago, Illinois. Now, let me introduce Mr. Baker. William Baker is a structural engineering design partner for the architectural engineering firm Skidmore, Owings Merrill, LLP. His work spans a wide array of structural engineering projects, ranging from small pavilions to the world's tallest structure, the Burj Khalifa. One of the focuses of his research and design is the optimization of structural and architectural geometry to minimize the embodied carbon of buildings. He has Honorary Professorship in Structural Engineering Design with the Department of Engineering at the University of Cambridge, where his research and lectures focus on design and on adapting the contributions of Rankine, Airy, Maxwell, and Michel to structural optimization and modern structural design. Baker's honors include being a member of the National Academy of Engineering, an international fellow of the Royal Academy of Engineering, the gold medal from the Institution of Structural Engineers, the Fritz Leonhard Prize, Germany, the Gustav Magnell Gold Medal from the University of Ghent, the Fazlur Rahman Khan Medal from the Council on Tall Buildings and Urban Habitat, and the American Society of Civil Engineers Outstanding Projects and Leaders Lifetime Award for Design. He has received honorary doctorates in engineering from the University of Stuttgart, Heriot-Watt University, Illinois Institute of Technology, and the University of Missouri. That's a brief outline of Mr. Baker's profile. Now, I request Dr. Jason Fitzsimmons, Academic President, Manipal Academy of Higher Education, Dubai Campus, to address the gathering and welcome Mr. Baker. Please, sir.
Thank you very much, Samaya, and welcome everyone to the fourth Tech Talk, and tonight's on the Burj Khalifa and the design of tall buildings. And one of the things we've always tried to do at Manipal is to work closely with industry and try to give students that real world experience from getting involved in what's happening in the real world there. And I think tonight's a very special night, and I think I'd like to welcome Bill to give the presentation tonight. It's indeed an honor to have someone of your caliber to come and give us a talk and share your experience in the real world. And I think it'd be a great inspiration to students and faculty alike to see what you've achieved in your own career there. And I hear that you're in Chicago, one of my favorite US cities there, and time difference. We have all the technology, but there's not much we can do about the time differences. So I'm sure it's an early morning over there, and I really appreciate you being able to do that and come and give us a talk there. And I think it's quite an impressive resume. When you think about the Burj Khalifa, it certainly put Dubai and the United Arab Emirates well and truly on the global map. And I think that it's quite an achievement to have it on your own CV. It's a great personal achievement, an achievement for your organization. And I think that what we'd like to do is welcome you to share your experiences, and I'll hand over to you.
Well, thank you very much for inviting me to give this presentation. And one of the things I want to point out is that I noticed that this is sponsored by the student chapter of the American Society of Civil Engineering. I think it's very, very important for all engineers to be active in the professional societies, both local societies and national and international societies. To push our profession forward, it takes active involvement of individuals. And if you go into practice, try to be active in your profession. you can help others, and you'll learn things yourself. So I'm very pleased to do this for the student chapter of the American Society of Civil Engineers. Anyway, so I'm going to talk about the Burj Khalifa and the design of tall buildings, and hopefully you can hear me clearly. If not, just let me know, and I can put on a headset if I need to. Now, when you talk about tall buildings, they're definitely part of our culture. There's always been the desire to go high. I mean, if you're if you're in the hills, you want to climb the mountain. You want to go see what's on the top. It's part of our culture going back to the Tower of Babel. It's central to who we are. We have this desire also just not only to go high, but to stand over the abyss. These are these glass boxes that hang off the edge of the Willis Tower, used to be called the Sears Tower, where you're a good 300 meters above the pavement, and skyscrapers there's some debate about what is the world's first skyscraper, but for the moment, let me use the home insurance building as an example. What makes it a skyscraper? There's two fundamental things, and these also apply to the Burj Khalifa. This was the first steel frame building. So the structural system and the elevators, the vertical transportation, as you call them, the lifts, okay? So on the home insurance, it was a steel skeletal frame. And then for the lifts, it was, Eliza Otis developed the safety elevator where you could cut the cables and it made it safe enough that people were willing to have it as the primary mean of getting up and down the building. And I have to say that structure and vertical transportation are still the key components of tall buildings. And the change in tall buildings, it went fairly rapidly from the home insurance building to the MetLife building in New York, and until we get to the Burj Khalifa, basically 100 years after the MetLife building. And so there's been quite a run up in the height. Though there was a bigger change from the late 19th century to about 100 years ago, the 1920s and 30s. Principally in New York, there was a great run up in height, and then the increase in the height of the world's tallest building was somewhat incremental for quite a bit years. And there's all these debates about whether or not you count the thing on the top. Is it part of the architecture or is it an antenna? And depending on how the buildings are designed, sometimes they're counted, sometimes they're not. But you can see it was a fairly steady range for the world's tallest building until you get to the Burj Khalifa, where the change in height was more than a 60% increase. And since it's a student presentation, I want to bring three technical issues to you. One is first a concept of a tall building. It's a giant beam coming out of the ground. Conceptually, this is very, very important. And because if you think of it as thousands of elements, like, these little columns and these spandrel beams and floor beams, it's too complex. Our brains are not able to deal with that information, and you cannot do the design. So, quite frankly, I do most of my preliminary designs with on paper with a HP calculator, a pencil and an eraser. Okay, and you can design the world's tallest building with just those tools. Okay, in the end, you're going to put in the computer to verify things and see if you missed something or get additional insights. But the fundamental concepts should be in your head. And let's talk about beams. So let's go back to the first structural theorist, which is Galileo. I consider him the first modern structural theorist. In his dialogues of 1638, he talks about the cantilever beam, and he gets it not quite right. He didn't figure out the neutral axis, but he got enough that he got the concepts right. So here we have a cantilever beam that's got coming out of this remnant of a masonry wall, and so let's take that idea to a tall building. Let's take a cantilever beam and turn it vertically. And just like on a cantilever beam, you push on it, it deflects. On a tall building, you push on it laterally, it deflects. And when we think of these tall buildings, we think of them very much in the context of a beam. In a beam, you'll have the flanges, which take the overturning moment. You'll have the webs that connect the flanges and handle the shear. And you know, in an I-beam, it looks like something we're very used to seeing. In a building, it might look like an I-beam, or it might look like a box or the like. And when I think about if I go back in our archives, when Dr. Fazler Khan and Hal Angar, who used to be my bosses at Skidmore here, you know, we're working on the design of the Sears Tower. Here, I found this in our archive. Here's a picture of the building, an elevation, the plan view, and this is a plot of the moment of inertia of the entire building. And furthermore, you know, it's a step function, but they approximate it with this linear approximation. And actually, you can get pretty close to the actual behavior of the Sears Tower just by using the simple principle of calculating the moment of inertia. And if you go down to the bottom of the Sears Tower or the Willis Tower, Faz Khan and Hal Angar called it the bundled tube. For me, it's actually a big box beam with 4 webs. And here are the stresses at the base of the tower. And with the wind going in this direction, you can see you have tension stresses along this edge. You have compressive stresses along the other edge. You have plane sections do not exactly remain plane. You know, about 30% of the deformations of the Sears Tower is due to shear deformations, and about 70% is due to pure flexural deformations. But it's acting very much like a beam. The second concept I want to throw out there is the importance of wind in tall buildings. Here on the left, you see this computer animation of fluid, in this case air, going past an object. And it goes by in a very irregular manner, first to one side and then the other. And on the right, you see a picture of the John Hancock Tower here in Chicago. And if you look, you can see a vortex forming in the cloud as it goes past the top of the building. This picture was actually taken by a scholar from Northwestern University. She's actually a Shakespearean scholar, but she got this great photo that I was able to get a hold of. And as these vortices appear, they will cause a pressure differential across the tower, which will cause it to move from side to side. And this happens in a very rhythmic pulse, just like a child on a swing. And so as you do that, you know, the child moves higher and higher because they're matching the natural resonant frequency of the swing. And this is the tall building problem. And it happens not only at the scale of tall buildings, it happens at the scale of a street lamp. Here you see these street lamps, they're kind of going wild. The wind is not going very fast. It's just a very steady wind in the wrong direction, and you have this harmonics. In fact, if a tall building were ever to fall over in the wind, it would probably fall over sideways. And because of that, we do a great deal of wind tunnel testing. This is actually a wind tunnel we have in our own office, and that we use for competitions and preliminary design. When we, towards the end of the building, we'll go to a commercial wind tunnel for the final design loads, such as RWDI that we use for the Burj Khalifa or other international quality wind tunnels. The third issue I want to have you think about when I talk about, I'm going to talk about tall buildings, primarily the Burj Khalifa, is issues of scale. This is very, very important. And this was actually recognized by Galileo in his dialogues of 1638. It turns out, for a long time, I thought this was drawn incorrectly. So here's a bone. This bone, the big bone, is 3 times as long and I think 9 times as wide. But it turns out if you had a pure cantilever where you're limited by the stresses, and the stresses are related to the weight of the bone, this is actually the correct proportions. It's interesting, Judge, just sit there, give yourself an assignment, do the math. on a cantilever with a circular cross section and with a given stress, and you make it 3 times as long. See how much deeper you have to be to have the same stress. Another important reference is this book, Growth and Form, which I urge you all to look at. It was done by a biologist, Darcy Wentworth Thompson, which is basically, he wrote it during World War I and revised it during World War II, but it's basically a lot of things in nature look like they do because of physics. And in many ways, tall buildings are also creatures in nature that should respond to the physics of their environment. Now, Galileo's rules weren't quite accurate for bone structure because it's not just a bending issue; it's also axial. But certainly, if you look at the scale of a small mammal to a tall large mammal, certainly you see changes in proportions, and at some point you just can't make it any bigger. That issues of scale don't apply. If I were twice as tall, imagine me twice as tall, and I'd be twice as wide, and I'd be twice as thick, and how much would I weigh? 8 times as much. So, things go bad fast. And so if I were to take the Sears Tower or the Willis Tower and scale it up to be as tall as the Burj Khalifa, it would be too big. You'd be too far from the windows, too much floor area. It just, you don't take this and scale it up. Whereas the Burj Khalifa scales by the square rather than the cube. And it's through this understanding of scale that I think we were successful in our design. Because if I were to make the Burj Khalifa twice as tall, I'd have twice as many levels. And I would have to make the legs longer, let's say twice as long, but I do not have to make the legs any wider. And because of that, it scales by the square rather than the cube. And this was an essential component of the success of the Burj Khalifa. So this is a diagram that Fazl Khan started years ago with his partner, my former boss, Hal Langar. And, and he, so he made this little charts of buildings, but I really consider it species. This is like you're going to a natural science museum and you're looking at different species of different tall buildings. And as the problem changes in scale, you need new species. And unlike nature, where generally, one creature evolves from another creature to another creature, in architecture, you can create completely new species as long as you're creative and you respect the physics of the problem. Here's some models we have of several of our buildings where we modeled only the structure. And in these species, in these creatures, one of the things I think is important to achieve as architects and engineers is that the architecture and engineering is so integrated that it's, say you pull the skin off the building, the architecture does not go away. They're the same. You cannot describe the structure without describing the architecture. You cannot describe the architecture without describing the structure. So let me lead you through the Burj Khalifa, which for many, many years we called the Burj Dubai, as you know. For us, it's the project started Saturday, March 1st, 2003. I and a couple of my colleagues flew to New York City to meet with some people from this place called Dubai about some project. And it was decided that by the client, Emaar, who, by the way, the head of Emaar, Mohammed Alibar, is one of the most hardworking people I've ever met. He's just, amazing person and a great client. Anyway, so we had a really quick, short competition, and we had just finished a tower in Korea, which was at one time 90 stories. It later got a haircut down to 73 stories, but it was this Y-shaped building, and it had a different system, not what we use in the Burj Khalifa, but this is the system we started with. It was basically kind of like a bundled boxed core, if you will, and this is not the system we ended up with the Burj Khalifa, but this is where we started. And so this is what we won the competition with in the spring 2003. And then, so we started out with, the brief was to have the world's tallest building. At the time, the world's tallest building was the Taipei 101. And so we were just, 10 meters taller than Taipei 101, which would have been the world's tallest building. But it quickly grew to 725 meters. And then after it was already construction, it grew to 828 meters. And I'll talk a little bit about how we were able to achieve that. How big is that? I mean, you guys live with it, but it's pretty big. Okay, it's interesting to see in the context of other locations. This is what it would look like in Chicago, or in downtown in New York, or Midtown in New York, or in Washington D.C. We call this maybe the Burj D.C. Here's what it would look like in the financial center of London, of the city, or out by Canary Wharf in London. Here's what it looked like in Paris, but I don't think you should ever put it next to the Eiffel Tower. The Eiffel Tower should stand by itself, but it would look pretty good in a lot of fonts, I think, if one decided to build it in Paris. Of course, here's what you guys are used to looking at as it looks in Dubai. The area in the tower is roughly 280,000 square meters, about 3 million square feet, which is big, but not that big. The World Trade Center towers that went down in New York, the ones that came down on 9/11, each tower had 4 million square feet. The Sears Tower, the Willis Tower, has 4.4 million square feet. So in that sense, the tower is in area sense, it's a big building, but it's not that big. And that's important. That's actually a good thing because that makes it more easy to market. The investment is more controlled as far as cost. And I think that's one of the reasons the building was actually built. Down at the base, there's a lot of other things going on, so parking and the like. So this is not including the mall or the other stuff. This is just at the base of the tower. And so the total project is on the order of 465,000 square meters. I'll walk you through the building. I'm sure you know it pretty well. At the base, we have these fairly large floor plates, to handle parking and other things. And then we get into the Armani Hotel, and then above the Armani Hotel. By the way, of course, let me give you a little look at the floor plate. The floor plate is this Y-shaped building, and what's remarkable is the views are great. If you go to the World Trade Center towers that went down, the columns were every meter, and the windows were only half a meter wide, and so it was like you were in a cage. On the Sears Tower, it was the windows are like 3 meters wide, and the columns are about 1.5 meters wide. So you're about you're about 2/3 window and 1/3 opaque. Here, these columns are on the order of 600 to 700 millimeters thick, and the spacing is 9 meters. So you have tremendous views. And as you're there and you're looking out, it's not like you're in. You may be in the world's tallest building, but you're not. Your views are not obstructed. Above the Armani Hotel, we have the this service residential, and then we have the more residential. The floor plates are changing as we go up, as they get smaller. The wings step in one at a time: A wing, B wing, C wing, in a clockwise manner. And then above there we have the luxury residential. Now Emaar, they were able to sell. This is just totally amazing. The yellow, the brown, and the blue in 2 nights in 2004. Okay, and everybody who bought a unit had to put up 50% of the purchase price within 6 months. And so that went a great deal towards financing the tower. One of the interesting things, when you're in a pure office building, your financial model is quite different because you have to build the entire building, get some tenants, and then wait for your rent check, okay? And so, whereas here, with the purchasers, your cash flow situation is much different, and that's fairly important, okay? So the floor plates continue to get smaller, and then at the very top we have these corporate suites, which of course now recently a lot of them have been converted into additional observation decks, including the chairman's suite. But at first these were supposed to be purely residential palaces in the sky, but fairly late in the game, Mohammed Alibar decided that he could do better if these were boutique offices for, as you guys know, Dubai is the financial center of that whole region. And so if, everybody in the region has an office in Dubai to do business. And so if you're very prestigious, you can have your offices in the Burj Khalifa. Anyway, so the floor plates are getting a bit small. And then you have to have these mechanical systems of floors. You cannot service all your mechanical and electrical functions from the base. The water pressures would be enormous if you had one pipe that went from the top to the bottom with water pressure. And the other thing, your transformers, you cannot you cannot take low voltage that high without too much loss. So what we do is we divide the building into, from a mechanical, electrical, and plumbing point of view, we divide it into a series of shorter buildings, say 30 to 40 stories. And this is very common in tall buildings. So that, and that's where you get your air to bring in for your services. You have your transformers, you have your pumps and the like. So you're able to use normal pressures, normal voltage drops within these zones. Another interesting thing to be, and I don't know if you've done this, but it's interesting, like in the summertime, is to be down at the base of the tower and then go up to one of the high terraces and feel the climate change. I remember during the construction, we used to go up on the outside of the building in the man hoist. And I remember going up in July, and you know how it is in Dubai in July, it's pretty hot, pretty humid. And by the time we got up to about the 50th floor, you start to notice the climate change. And by the time you got up to 160, it was pleasant. And so and so our mechanical and electrical, our mechanical engineers took advantage of this. We call it sky source sustainability. They took advantage of the cooler and drier air up high for their intakes at the top of each of these zones. As I said, structure and vertical transportation are key aspects. So I'll give you a little map of the vertical transportation. And what it is, you have a series of, for the bottom zone, it's like a normal building where you go in and you take a lift to your individual floor. For these upper zones, what you do is you kind of take like an express elevator, we call it an express lift. And then you get, it's like taking an express train from one major city to another major city. And then you get in the local train to take you to your village. And so that's how it works. You have these express lifts that take you to a sky lobby, and then you get in your local, and it goes very fast. It was interesting for the top zone. We actually go up to the middle of the zone, and then you get in your locals. They either take you down or they take you up. Now, at the time when we did the Burj Dubai, as was called at the time, Burj Khalifa, the highest you could ever go on a lift was 0.5 kilometer. And so that is what we did here. And so this gray bar is the freight elevator, the service lift, and it goes up 0.5 kilometer. Then you have to change into a local to get to the very top. Nowadays, they've come up with new technology using Kevlar cables instead of steel cables that they could actually they can go 1 kilometer or more. Okay. Certainly the fire-related safety is very important. And so people, if they go down the stairs, they can do it in these protected stairwells. There's multiple stairwells. I've never climbed all the way up, but I've climbed down. I remember when it was under construction, I had one of the engineers give me a little chart of all the link beams with the highest stress. So I was looking for cracks. At the time, there hadn't been any big windstorms, so I couldn't find any cracks. But I walked down. It took me a while, but it wasn't too bad. My calves hurt the next day, but coming down, it's not too bad. But we don't expect people to come all the way down. We have areas of refuge several times down the tower where someone could get out of the stairwell, take a rest, and then continue their trip down. We also have something called lifeboat elevators, so people can, with the permission of the fire marshal, you can take some of the elevators can take you down even if the building has an emergency event going on. Okay, so what make this possible? Number one, good luck. Okay, the right place at the right time with the right client. Okay, but let me keep it to the technical side. Okay, so what made this possible? Structural systems, the wind engineering, the integrations of systems, and the construction technology. And so, as you probably well know, it's primarily a reinforced concrete building with the steel, with the top it transitions to steel for the spire. It's composed of simple systems, walls, slabs, and a few columns. And if I were doing it again, I wouldn't even have the columns. I just have walls and slabs. This is the structural system. As designers, as you go into work, you need to be in control of the design. If your boss asks you how the structural system works, and you have to go query the computer, you're not in control. You need to be telling the computer how the system works. Okay, and you need to be driving the design. And if someone asks you to describe your design and it takes lots of words, maybe you're not there yet. What you need to do is you need to distill your ideas down to their essence. And Faust Kahn did this. I don't know if he did it intentionally or just innately. The John Hancock is a braced tube, 2 words, noun and an adjective. The Sears Tower is a bundled tube, 2 words, noun and adjective. And you don't want to do this too early because you don't know where you're going when you start design. Design is very nonlinear. But at a certain point, when you think you're close, you think you're there, try to describe what you've done in words. And if it takes a lot of words, you're probably not done. If you get it to a few words, that's good, like maybe a sentence. Sometimes you can get to 2 words. And so the essence of this building is a buttressed core. So the core, this hexagonal concrete wall system in the middle, is very important for torsion. You do not want to have a tall building twist. So that this acts like a giant axle that keeps the building from twisting. But it's too slender to go to much height. I think it's like 11.6 meters from the center to one of these cross walls. Anyway, so what we do is we buttress it by these kind of like parts of an I-beam going down the 3 wings. Just like an I-beam has a web and flanges, this has web and cross flanges in the 3 directions. If the wind blows against 2 of these, if wind pressure against 2 of these wings, the 3rd wing will be the buttress to resist those forces. And this acts like a giant beam. We actually calculated the radius of gyration of the entire building as part of the design process. And this man represents the lateral system of the Burj Khalifa. He's resisting wind against the umbrella. His front leg is like this core, and his back leg is the buttress. So this is the lateral system for the Burj Khalifa. Now, one of the most important things you need to do in a tall building is manage gravity. Gravity is very reliable. You can count on it. It's you don't worry about the inspector for not being there that day or anything like that. They will, the gravity will be there, but you need to put the gravity where you want it. So what we did a lot is this is from the core to the perimeter. We pushed the gravity outward, and in the process, we had to do a lot of we had to push that gravity across these link beams in order to get it out there. So we did a lot of research with the University of Illinois, did some studies, and we had three kinds of link beams: normal, reinforced concrete, then with a encased steel plate, or maybe a very large encased one. And for each of these, we did a series of studies. Sometimes we could just use strut and tie, and that would get us pretty far. Sometimes you could just use the normal equations, but usually we had to go to strut and tie. And on the right, you can see the capacity we had, or should I say, this is the red line is the demand, and these curves are the capacities. And then we put it in a plate. Once again, here's the demand, here are the capacities. And sometimes we put in a really big plate. Okay, and once again, the demand and the capacities. But we thought it was very important. Nowadays, there are like codified rules on how much to embed the steel plate. And so at the time there were not, so we were doing fundamental research to come up with these values. Anyway, so what it is, this is what the rebar looks like at the bottom of the Burj Khalifa. If you were to walk up to that as an engineer or an architect, and you look at that rebar, and someone asked you, well, how tall do you think this building is? What would you say, 5 stories, 10 stories? You probably wouldn't say 160 stories, 160 plus stories. But the Burj Khalifa has no tension, even in a storm that happens once every 1,700 years. That's because we manage both the wind, but also manage the gravity. We use this amazing material, which we call reinforced concrete. We should probably come up with a new name. At the time, Dubai has really good concrete, by the way, compared to many places in the world. Part of it has to do is because the corrosive soils there. So the way to beat that was to have a high quality concrete, and so we designed it for kind of the highest strength concrete that was kind of available at the time, like a C80. Though the supplier generally delivered at least C100, very high modulus, so really good stuff. It's like I say, it's not like the stuff that's down on the sidewalks for sure. We were very concerned about creep and shrinkage, and so we actually controlled the surface volume ratio and the mixed designs of all the vertical elements so that they were all within a very narrow range. We calculate how much the building change dimension. Like this is level 147. This shows the creep and shrinkage study. At the very top, we had the steel spire where this triangular system set on the hexagonal core. At the very bottom, we have this foundation system of piles. You notice most of the piles are outboard, not in the middle. And we're in this. These piles are 1.5 meters long, about 45 meters deep. They have around, I think it's 194 piles. I have to count them again. Settlements are very small, about 50 millimeters, only that much. The width of 2 thumbs. That's how much the building settled. We're sitting on. You guys have a sedimentary rock called calcisiltite, which is, in my mind, is like sandstone, but instead of sand, it's silt. It's seashell silt. It's a calcium silt. And it's pretty good material. And occasionally, you'll have a gesiferous void zone, but we didn't have that problem. Where you might have some voids, but there were no voids. Let's go back to the wind engineering that we talked about before in the harmonic resonance. And so we did a tremendous amount of wind tunnel studies. The minute we won the competition, we went into the wind tunnel. We had to figure out what the wind climate was in Dubai. There wasn't as much data today as we had by then as you have today. So working with RWDI, they made what we call a superstation, where they took the wind data from several airports in the region and made like a pseudo superstation. And then they did a very sophisticated studies to figure out what the velocity profile is as you get higher and higher. We did a whole series of wind tunnel studies, and with various configurations and various structural systems. And what we came out of, the building has 6 principal directions. When the wind blows into the nose, it's pretty benign. The nose acts like a cutwater, and the vortex that's forming forms downstream, so it doesn't really push against the building. But when the wind blows between 2 of the wings, we call that the kind of the tail direction, a vortex will form and blow against the 3rd wing. And that was of some concern. And so what did we do? We reshaped it, and actually, you know, the first shape we tested, the wind tunnel, did not work. It had very, very big forces and very big motions. And so what we did is, you know, if you've ever read The Hitchhiker's Guide to the Galaxy, it says, the guide says in bold letters, don't panic, okay? So as engineers, when you have a problem, don't panic. It will not help you. Work the problem like an engineer. Figure out what the problem is and work it and try to keep calm. And so what we did is we reshaped the building. So every time you change the shape of the building, the rate of the vortices is changing. And so remember that child in the swing with 2 feet that are kicking in harmonics? The Burj Khalifa essentially has 27 feet, and they're all kicking at different rates. So the swing doesn't go anywhere. The harmonic action is barely activated. And so this red line represents a 100-year storm. And so our first shape was like, these are the 6 directions. By the time we had reshaped it, twice, from wind tunnel study 1 to wind tunnel study 3, the forces had dropped. My little bar moved a little bit from here down to there. And all of a sudden we could go much higher. And so here are the, some of the wind tunnel models. We have both air elastic and what we call force density. This is the first model. This is an intermediate. This is the one we built. We actually tested one that was taller. That did pretty well, but it was too late to accommodate it. We then tuned the building. We tuned the harmonics of the building like a musical instrument. We play with the mode shapes, which directions it shakes, what's the fundamental mode shapes, what's the period, and what's the shape of the mode shapes. And we had very, very good dynamic behavior. And then the air elastic models, which actually model the actual structural harmonics with this milled bar. And here's what we found. So here is the one right after the competition. Base moment, let's consolidate that force. Acceleration, how much movement is done. By the time we finished the building, even though the building grew by 310 meters, the change in height is essentially the height of the Eiffel Tower. The change in height equal to the Eiffel Tower. The base forces were less, and the motions were less. What's really strange, this other one, which we didn't build, was actually even better, but there was a hot spot around the 40th floor, and we'd already gone past the 4th floor, so we didn't avail ourselves of, we weren't able to avail ourselves of this. One of the things that came out, as engineers, you'll get exposed to scaling and similitude, it's called. And as you go from in the wind tunnel with the tall building, you can scale everything but the air. You can scale the geometry, the harmonics, but you cannot scale the air. And but if you're in a turbulent range, it shouldn't make any difference. So these are the wind speeds, the model wind speeds, and as we change in meters per second, and what we did is as we changed the wind speeds, it went down, then suddenly stabilized, which indicated we might have a problem, an issue with what we call Reynolds number. And so we did this model up in Canada at the National Wind Tunnel in Ottawa, And it's a pretty big model. Okay, it's a 9-meter high wind tunnel, and so we did this test just to see if we had a Reynolds number problem. These buildings are Swiss watches. Okay, everything matters. And so this is the core. This is we have it. The most shafts we have it has 54 lifts, but the most openings for lifts we ever have is 19. Because there's double deckers and the sky lobbies and stuff. And everything has to be precisely oriented. And so the architects and engineers go back and forth. It took us weeks or months to get this right with the architects and engineers proposing and counter-proposing, how to lay out the core. And so you have all these pipes that have to get through the structure. So you have to provide holes for them. And so if you want to design a tall building, number one, have a clear structural idea. Do not try to make a bad idea work. Okay? So you got to have a rational system. You got to think about proportions and scale. We owe it to our society to be efficient in the use of our materials. You got to manage wind and gravity. And perhaps most important in really tall buildings is it's got to be simple and fast to construct. You got to have at least one idea how to build it. My boss, Hal Langer, used to always say, don't propose a design unless you have at least one idea how to build it. Now, it doesn't mean you have to be a construction expert, but you can talk to some of your buddies who go into construction management or something, say, I got this idea, how am I going to build it? Okay. And they're usually, buy them a cup of coffee and then maybe they'll help you out. Okay. So this is what we had. Here is our pile load test, your typical 6,000 ton, which is not typical at all, 6,000 ton pile load test. We never failed a pile, so we really don't know how strong our piles are. We know they're at least 6,000 tons, okay? In Dubai, you have very, very corrosive groundwater, so we did cathodic protection on the foundations. We did our test cubes here, 3.7 meter test cubes, where we tested, this is for the foundations. We were looking out for heat of hydration issues. You do not want to have your concrete cure so quickly that you change the chemistry. If you start to boil these things because the heat, you got problems. And so you have to have a mix that will, and of course, they always want to, no matter what, they always end up doing these massive pours in the middle of the summer. So, you gotta take that on head on. We poured the foundations in these 4 segments. There's the rebar cage. There's the concrete of the mat. And then it sat there for a while. For those of you guys who know Dubai, the neighborhood's changed a little bit, okay? Look at that. It's all desert, okay? You go to that, you go there, it's, you recognize some of the buildings, they're up the coast, but, Anyway, so it sat there. So the foundations were done ahead of time by another construction team. And then it sat there while Emar and Mohammed Alibar negotiated with, I think we had 7 bidders for it because we used very conventional construction technology. And this was on purpose. We knew we were going to do the world's tallest building, and we needed to do it with structural systems that were familiar to contractors. And so we had 7 valid proposals, tenders for the project. Anyway, so eventually a team was selected. First thing they did is they tried to figure out how are you going to pump concrete 600 meters in the air. And I was thinking, how are you going to do that? You're going to go to a mountain or something? No, what they did is they used hydraulics, Hardy Cross. And they figured out about how many bends and going back and forth across the desert floor will you get a pressure loss, which is equal to pumping vertically 600 meters. And they tried various concrete mixes and looked to see what came out the other end was still concrete or not. And eventually I came up with a concrete mix so they could pump 600 meters. So here's what it looked like when Samsung, Arab Tech, and B6 showed up on the site in 2005. And then it goes off to the races. It's like a vertical factory. The formwork raises itself. The concrete is pumped. The only thing that has to come up on the hook for the structure is the rebar cage. The walls and the slabs can be raised independently. That's very important for speed. And the wings were left, the tips with the columns were left behind because they took too long. And it went up. The original cladding supplier went bankrupt, a Swiss group. And then later they brought in a group from Far East Aluminum to do the skin. And it went up and up. We couldn't get a crane high enough to build the spire from the outside. So it was built on the inside of the building. So this is the bottom of it. We had this kind of like, I call it like a lazy Susan at the bottom, where it was a triangular opening going up to the tower. And then this base, you get to the place and you rotate it 60 degrees and set it back down. Anyway, so here it is hanging on strand jack down into the building. And it was, launched out the top. We even put blades on the top of the spire. If you look close, you'll see these blades. That's to break up the vortex shedding on the spire itself. Of course, there's a light up there. I understand Tom Cruise changes the light for them. I'm not sure about that. That's a joke. Okay. Anyway, so there you can see the very top. It is the lightning rod for your entire city. Okay. I'm sure you've all seen it hit by lightning. Of course, it's completely grounded. It's a giant Faraday cage from your physics or electrical engineering class. So lightning can never get into the building because it's a Faraday cage, and it's grounded, so it does no damage. There was finished before they washed it. You're certainly above the clouds occasionally. And then they washed it and it looked beautiful. Just amazing. And all that brightness you see is light not going into the building. It's actually a hexagonal, so there's no more than 1/6 of the building that's ever directly in the sunlight. All the other 5 faces are opaque to the wind, and then you have these bright mullions which reflect the light, and the glass itself has what's called a low E coating that lets in light, but keeps the infrared light out. The heat keeps the heat out. Of course, you get to see it. I don't get to see. I haven't seen it since a couple of months before the pandemic, so I haven't seen it like almost a year, not quite a year and a quarter or something. It's incredible the way it catches the light. Of course, then we had the grand opening on not quite 11 years ago. It was Independence Day, January 4th, 2010 was the grand opening. They announced the height was a big secret, and they changed the name from Burj Dubai to Burj Khalifa, which was a big secret. No one knew that, No one knew the name, that the name had changed. It was always called the Burj Dubai. No one knew the name had changed or the actual height until boom. So this is the instant that it was announced. They had the fireworks, just totally amazing. It was a nice event. As architects and engineers who go into design, we don't actually build the buildings. We do the drawings. These are the people who build the buildings. It was Samsung Construction, KJ Kim. He led the thing. So the #1 guy was from Korea. The #2 guy was from, he's actually right there behind him, was from Belgium. The #3 guy was from Korea. The #4 guy was from Belgium. And then Arab Tech provided most of the labor. And then this is, he was from the owner's rep side. This is, I think, what's his name? I think he was on the local inspection side, and he was from Turner, who was on the owner's rep side. And this is my back. Okay. Anyway, so these were the main players on the structural side. I'm running out of time, but let me say briefly why super tall. Dubai is the reason. Okay, and we are in this area super tall. These are the buildings taller than 200 meters of the last century. this century, last century, this century. We're in the era of the tall building. You know, and every year, you know, there's some very tall buildings built. These are the buildings that my firm has done. We think will be completed in the next few years that are all over 300 meters tall. You know. And you know, I feel a little embarrassed talking about this to this crowd, but you know, the Burj effect is a big deal. Okay, around the world, you know, there's that desert. This is my last time in Dubai, like November 2019, I guess it was. This was the last time I was, you know, I haven't traveled for a year now. Anyway, so I took these photographs as the night went down. I was over there. I did a little thing with Richard Hammond from the Top Gear thing, where we kind of rode dune bugs across the desert and tried to explain why that matters. Anyway, so they're okay, and then the shows, you know, the people, the crowds, you know, the fountains, the music, you know, and the light shows, just totally amazing. You know, when you think about what this building has done for Dubai, the UAE, and for the world, it's just quite amazing. So, thank you.
Thank you, Mr. Baker. That was really wonderful. So now the forum is open for discussion. So students and participants, kindly type your questions in the chat box, or please raise your hands for asking questions.
Yeah, and I have a little, I'll turn off the, I'll stop sharing for a moment. But if you could help me monitor the chat box, because sometimes I don't keep up with it very well.
Sir, at the below, you can find chat.
Yeah,
at the bottom of the screen, you can find it.
I'd love to hear from you guys. I'd love to hear from those of you in Dubai. Sure. If you have any experiences or things like that. Whenever I go to the Willis Tower, I always talk to the tenants and ask them, well, you know, how's it going? You know, and so if you have any stories, or if you think of something later, just drop me a note. But you know, it's always, you know, the Burj is instrumented. It's heavily instrumented. You know, so Samsung, you know, took the lead on that, and you know, and it's a very sophisticated operation there. Particularly on the, you know, it's almost the way they're monitoring and managing their mechanical systems and their elevating systems and their electrical systems and their plumbing systems, very, very sophisticated.
Yeah, hello. You can hear me?
Yes.
Yes, so I'm an architect and faculty at the School of Design and Architecture. Thank you for a very, very insightful and amazing session. And I would just like to say Burj Khalifa is my favorite building, and for many others. As you started saying that concept, wind, and scales are the three major issues for any tall building, and architects always conceptualize and design buildings. And we often credit the design of buildings to the architects, and engineers always complain about it. But the role of engineering in this mega structure is amazing. And I would like to ask you that, was there any conflict or any design changes or challenges that the architects had to do because of the engineering barriers or challenges that were there during the process?
Well, I mean, it's an interesting question. You know, my firm's a little, is an integrated firm where we have architects. You know, so Skidmore, Owings Merrill. Skidmore was an architect. Owings was an architect. Merrill was an engineer. And so, you know, we're an architectural engineering firm. We have, you know, urban planners, interior designers. Interior designers were very active in this project. You know, they were, you know, a lot of it, you know, was, and so, you know, we do a lot of tall buildings. Okay, so people know, you know, sometimes you have to give the right of way. You can sort out who gets the right of way, what's more important. and one of the reasons that like I like giving a conceptual name like the buttress core, it helps you sort out conflicts. It tells you what's the essence of this thing. Now, other things we can modify, but there's some things you can't or you shouldn't. And so, we had like 2 rules starting on at the very beginning, which was no transfers. All the structural elements had to line up from top to bottom. You couldn't move sideways. And number 2 is stay on module. There's a joke that SOM, my company, Skidmore Owings Merrill, SOM means stay on module. Okay, so we had a 9-meter module, and so that was a very rigor. That because if everything can change, you'll never finish the project. It's too much. And so no, this is very much the architects and the engineers. We're like hand in glove. I mean, we sit together. We go to the coffee machine together. We socialize together. So there's this continuous interplay, and we do many projects together. And so it was like, okay, and my principal, and this is also true for the mechanical engineers and the electrical engineers, the plumbing engineers, and interior designers, urban designers. Anyway, so let me go back to the problem where the building didn't work at the beginning. Okay, so I got the raw data from the wind tunnel, and I started studying the data, and then I could start making interpretations. I was looking at both it's kind of like a mechanical impedance plot. It's kind of a mechanical engineering thing. And so I was looking at that, and I was making interpretations. I was looking at the climatic data at the same time. And so, so the engineers and the architects and the wind engineers got together, and we got together. We said, okay, we need to rotate the building 120 degrees because it's, there's certain wind directions. And we need to turn, and we need to change. The setbacks used to go counterclockwise. We need to change them to clockwise. And we need to keep modifying the floor more. And so then the architectural team took that and work with that, and then they would show us, and we would comment. But they laid out the floors based on our input. And, in a tall building, I talked about the wind thing. The single most important structural parameter is the architecture. What you architects call the massing, the shape, absolutely critical. So the reason we were able to go so tall is because the architectural massing was responding to the structural demands, and it actually makes the building more interesting. It had no way was the architecture diminished; it was actually enhanced, by this process. And so, and when you end up with a building like that, like the Burj, and when you're in super tall, everything's got to be humming. Okay, you got to be, there is no room for having subpar systems. All the systems have to be right at the edge because they're very expensive, and you can't be wasteful. But you also have to compromise. Not every individual system is totally perfect. Because you have to know that when you can give to help solve one of the other discipline's problems, and this whole thing about the core, designing the core, the architects did the first pass, did not work for us structurally, and so we redesigned it, but we didn't know all the things the architects knew, so we gave them our sketch and said, well, that doesn't work, but they saw what we were trying to do and they redraw it, and this went on for, I would say, over a month, maybe 2 months, I don't know, at least 6 weeks, this design, proposal, counter proposal between the architects and engineers. And the most important thing is mutual respect. Mutual respect, and also do not underestimate the creativity of your collaborators. Sometimes we would say, well, we could do this, but could you solve it on your side? and let them go back, and then you can say, well, we can solve it structurally or we can solve it architecturally, and then and then what's best for the building. And so, anyways, but it's a very important point, particularly for students. And if you go into firms where you're different consultancies, say you're a firm of only engineers or a firm of only architects, somehow develop relationships, even though maybe you don't get to go to all the meetings or stuff like that. And if you're in an integrated firm, really interface with your other disciplines. It has to be a personal thing, not just where you're learning from them. And after a while, engineers can propose architectural solutions, and architects can propose structural solutions because they've seen so much. They understand it. They're not just doing what they've been told. They know why this is so. And you learn that from your colleagues.
Thank you.
Hello, my name is Basil Ismail, a fourth semester civil engineering student. First of all, it's a great honor to be a part of this great event. And my question is that, as you have said, Burj Khalifa's different cross sections never allows the wind to organize. What are some other ways to configure a tall building without the wind forces resonating in its natural frequency?
That was a little, could you say it again? I'm going to get closer to the mic this time.
As you have said, Burj Khalifa's different cross section never allows the wind to organize. What are some other ways to configure a tall building without the wind forces resonating in its natural frequency?
Well, there's the two sides of it. There's the input variable, which is your input force, which is the wind, and then there's the structure. So you can play with both, or the dynamics. So you have stiffness, mass, mode shape. So you can play with your structural properties, and you can play by shaping the building. You can play with your wind forces. You can have holes go through the building. If you have a hole go through the building, then the wind will short circuit through the building. You can have eroded corners. Sometimes you may just have a big shape that has big forces, but if it has high levels of mass, or part of it has to do is at what wind speed do you go through natural resonance? Okay, if you have a very small floor plate, the wind speed that will cause natural resonance may be a low wind speed, so that it may be a concern for occupant comfort, but is not a concern for structural forces. Here's a little bit of a bad example. I used to have a 1966 Ford Custom 500. Okay, it was a six-banger with a three-speed shift on the column. Anyway, the wheels were out of alignment. Okay, and so when I would drive, when I get up, I'm sorry for the U.S. units, I get up around 50 miles an hour, the thing would shake like this. But when I went up to 70 miles an hour, it smoothed out because I went to the other side of resonance. And so you can do that in a tall building. You can play with the shape and then the tune. Sometimes you want your building to be softer, not stiffer, depending on when you're going through the natural resonance. And then mass helps. You can also put damping devices in there. The Burj Khalifa does not have a damper, but we left room for one in case we need, or we figured out how we could add one if we needed to. And because as an engineer, you need to not be too conservative, but ask yourself, well, what if this isn't quite right? That you haven't, as they say, painted yourself in a corner you can't get out of. And so, all the data told us that we did not need a damper, but it was a pretty tall building, okay? So we figured out a way that one could construct one if one needed to, and you could bring it up through the freight lifts, service lifts. But in the end, we didn't need them. So, all right. So, but part of it is do lots of wind tunnel testing, and don't just let the wind engineers tell you the answer. Get into the data. Analyze the data yourself. Anyone else?
Sir, I have a question.
Yes.
I'm Javed from Computer Science Department. I'm not a civil engineer, but I have some, because I've seen the video of the Burj Khalifa construction stuff. Really amazing work. Your contributions were really amazing. Very excited to hear the entire conversation. Sir, actually, see, as per the height, the water is not pumped to the top level in one attempt, right? It is going to the different stages. So that means you have a different tanks in different levels. Correct. If there is a heavy wind, so what happens? I think I've seen there is a swing in the entire structure. Suppose if a vessel is having a water, which is if I move that vessel, there is a force will be acting on that. Correct. So how it is managed in the entire structure? So because of the swing, there is a possibility more pressure in the swinging side. So how it is managed? How it is not?
Well, I mean, actually, sometimes not in this building, but there are buildings around the world where they have what they call sloshing dampers, where they actually use water tanks that slosh back and forth to dissipate energy. They put baffles in there. But the Burj Khalifa is a very quiet building. And it has a very long period, 11 seconds. So it moves very slow. You actually, the Willis Tower moves a lot more than the Burj Khalifa. The Burj Khalifa, and so, and you can look, and you can calculate the harmonics of the tank. And it's actually kind of difficult to get the harmonics to match 11-second period. I mean, you'd have to have certain proportions, which you're not going to have in a normal water tank. And so the amount of movement is pretty slow. The other thing is, this building is a very, very pure beam. In a lot of buildings, which like say beam, like they have a moment frame with columns and beams, you get a lot of, like we call it shear racking. But in the Burj Khalifa, except at the setbacks, there's almost no shear racking at all, because it's you have all these walls, and so your shear deformations are tiny, and so you don't get near as, it's really one of the most benign buildings in the world, tall buildings, as far as it's really quite. In the end, also, by the time we did all the reshaping, the wind forces are really quite modest, even though it's so tall. So it's got a very gentle period, and for that reason, a lot of these issues are not issues.
Okay. Fantastic. Thank you.
Okay.
Mr. Baker, it's already 8:15. I mean, we have passed 15 minutes than the time limit. So is it okay for you to continue for 5 more minutes so that our students can ask a few more questions?
Yeah, I'm fine.
All right. Thank you.
Yeah, I'm afraid I went a little long. I always keep my watch next to me, but I talked a little bit more than I intended to.
That's fine.
So if there's any more questions,
Yes.
and quite frankly, if somebody has any personal experiences they'd like to share, you just drop me a note, or you can send it to the organizers, and they can send it to me. Because I'm always looking for feedback. I mean, we do have the building's instrumented, but still, I like to hear human feedback also. Okay. So,
yes, we have a question from Mansoor. Or Ali?
Yeah, can you hear me? Yeah, hi,
Yes.
Mr. I'm Ali Hussain. I'm a sixth semester civil engineering student. Um, and thank you for taking out your time and talking with us on such a vital topic. So, basically, my question is it is well known that high rise buildings indeed have a lot of benefits that are associated with it. But recently, I came to know from various news outlets that a country like China has capped the height of the high-rise buildings in an effort to protect the local culture and enhance the spirit of the city. So also, I went through some of the scientific studies on that document the sociological impact of high-rise buildings on the people and the culture. So, what do you think on this? Like, should the concerned authorities should correlate the projects with the humans' need, humanitarian balance, and low impact on biosphere?
Yeah, let me speak to that a little bit. The Burj Khalifa is a different situation because you're creating an event, okay? Just like the Eiffel Tower is, you might say the Eiffel Tower is a very expensive way to make a restaurant. It's more of a creation of a place. And that's what the Burj Khalifa. In general, density is good for the environment because people live close to they live and they close to where they work or where they shop and the like. The Sears Tower has 100 acres. Let's see, divide that by 2.5 to get to hectares. I guess 40 hectares of floor plate on one city block. Versus being in the suburbs where everybody has to drive to it. If you're out in a low-rise building and you drive to work, the size of your parking space is bigger than your office. Okay, a typical parking spot's about 27 square meters, which my office is not 27 square meters. Okay, and so there's so that's part of it. Now, in China, the limit is still pretty high. It's like 500 meters, which is it's taller than and that was kind of done, I think, just because they were like a little. That was done by the premier. I think it was just because part of it there was a bunch of silly buildings going up, and so I think it was more done for that point of view rather than any other cultural things. Because I do a lot of buildings in China. I think I've got. I just finished a 530-meter tower in China. I got two 500-meter towers under construction now. I'm doing a competition for another 500-meter tower right now, and so they're very much into it. So the limitations in China were more about trying to calm the market down, if you will, and also there was a lot of, I would say, frivolous designs going up. They're perhaps not. I think they're becoming more carbon conscious than they were. Their pro formas were a little bit more generous than what you might have in Dubai or Europe or the U.S., where developers are more serious, or the margins are smaller or something, or the cost is higher. I think that's part of it. But I do think density is good, but it doesn't have to be that tall. Quite frankly, 30 or 40-story buildings, you can get a lot of density. Okay, if you go up to, there's a lot of density in Dubai. If you go up to the marina, there's a lot of density there. Okay, and it's really about getting people where they're not in automobiles. They're taking mass transit, or don't have to take mass transit at all. They can walk to where they shop and where they work, and from where they live. And so that's a big part. Before we wrap up here, let me just throw in one thing there for since there's a lot of students here. I was reminded by the last speaker, who's sixth semester, is one of the most powerful things a student has is the ability to be poor. Okay, you guys are used to being poor. You have living without any money. Okay, and the advantage of that, you have freedom. after I graduated, I went to work for a while, but I didn't change my lifestyle. And because of that, I could go back to graduate school, or I could change my profession, or whatever I wanted to do, because I had not picked up a lot of debt. I hadn't bought fancy cars or fancy houses, and where I no longer had the freedom to change my mind of what I was going to do in my life. And so when you're young, try to maintain your freedom as long as you can. So if you decide you want to change your profession or change your focus, you have the ability to go back to school and do that. You're not encumbered where you have to keep working just to pay your debt. So that's one thing. The other thing is, if you're going into structural engineering, you really need a graduate degree. You just can't get enough education, and even a master's degree is a little bit on the light side. As I said earlier, I worked for 4 years, not in structural engineering, for an oil company, but I wanted to get back into structural engineering. But I did work a little bit on the periphery of structural engineering, kind of as an owner's rep on some construction. And the thing I learned from my working is that I didn't know anything. My biggest takeaway from my 4 years is that I didn't know anything. And so when I went to graduate school, I first took all the classes I needed for getting a master's, and then I spent a whole another year just taking more classes, because I knew it was unlikely I was going to go back to school again. And that second year of getting that extra depth of knowledge, if I hadn't done that, I probably would not have done the Burj Khalifa. Okay, so and I have to say, theory is practical. If you're going to design something that's never been done before, you need to know the fundamentals of engineering mechanics. So I'm a big supporter of understanding the theory, because we now live in the computational age, and all you particularly your engineers here, it's been over 40 years since I graduated. 40 years from now, what is the world going to be like for you? We're going to be in the post-computational age. Right now, you need to know how to do the computer, Rhino and Grasshopper and all that good stuff, all the finite element programs. But towards the end of your career, what it's going to be about is your ability to interpret, your ability to understand what it is the computer is telling you. That you can see what's happening because you have the knowledge, the ability to interpret. And that's the stuff that's not going to have a shelf life, is your fundamental understanding of engineering. Okay, so that's my little soapbox there at the end.
Hi, I'm Sheha, 6th semester BTech Civil Engineering student. Mr. Baker, here are many structural engineers listening to you today. We highly value your knowledge and wisdom. I want to ask you, what one advice would you want to give us, the civil engineers, pertaining to our careers, networking or academics? And what have you done extraordinary during your academics, which took you to this height?
You talk about essentially school versus work? Is that the question? The academy versus the practice? Is that your question? Sorry?
Academic or networking?
Well,
civil engineers pertaining to our career. Yeah.
I think I understand the question, but I may not actually answer your question because I'm not quite sure I understood it, but here goes. Okay. I think you're asking about the academy versus practice. By the academy, I mean, the research world. I'm always involved in research, 100% of the time. Mm. I had a 2-hour research call this morning where we're trying to invent new ways to design grid shells. And also, if you really want to learn something, try to teach it. The professors can really attest to that. Okay, if you think you know something, write a paper, and you'll find you got all these holes. Try to teach it. You'll find out you really don't understand it until you try to teach it. And so that's part of it. And it's really good but also practice is very important, because then you get grounded into what matters. So I think doing both is important. I had a feeling that wasn't your question, but go ahead and ask again if if you want to say it a little bit differently.
Thank you so much, Mr. Baker. That was marvelous. I'm sure we have learned so much in the time we've been here. And it's time to wind up. I request Professor Susan John, Faculty Coordinator, ASCE Student Chapter, to deliver the concluding remarks. Ma'am.
Thank you, Dr. Surmi. On behalf of the School of Engineering and IT, Mahe Dubai campus, and of our ASCE Student Chapter, I would like to extend our deepest gratitude to Mr. Baker for your enthusiastic participation. It was a very instructive and illuminating talk indeed. Your years of experience, depth of understanding, and expertise in the design of tall buildings are certainly a source of motivation to all the faculty and students here today. I would also like to take a moment to thank Ms. Stephanie Wagner, Executive Assistant at SOM, for her support throughout the planning and organization of today's event. My heartfelt gratitude to Dr. Jason, Academic President, for his support and presence here today. My sincere thanks to Dr. S.K. Pandey, our Dean, for your continued encouragement. Lastly, we are very grateful to all who are present here today for being such a wonderful audience. Hope you had a great time tonight. Thank you all. Thank you.
Okay, cheers. Bye-bye.
Bye.
Bye-bye. Thank you.